So first, welcome everyone to I guess this is the afternoon session, depending on your time zone. So our first speaker this afternoon is Anthony Ashmore from the University of Chicago, and he's going to tell us something about numerical metrics and the connection to the swampland distance conjecture. Take it away.
Great, thank you. Can you see my screen? That's all okay?
Yes, it looks good.
Perfect, thank you. So first of all, let me just say thank you to the organizers and the speakers so far for putting together a really lovely set of talks in such uncertain times. So today I'll be talking a little bit about numerical metrics, how you can use these metrics to compute spectra of the Laplace operator on Calabi-Yau spaces, and then a sort of first use of this new data to explicitly test the finite swampland distance conjecture, in particular in the complex structure moduli space of a particular quintic Calabi-Yau threefold. So this is mostly based on work with Fabian, who's here in the audience, and also some related work with Nima Afghani-Jedi and Clay Cordova here at UChicago. So in string pheno, we don't need much motivation for studying Calabi-Yaus, but for the new people, obviously, Calabi-Yau manifolds are important in both mathematics and physics, and are particularly useful for deriving semi-realistic models of particle physics from string theory. In particular, when trying to understand string theory vacua that are physically acceptable, we usually focus on sort of coarse information such as the gauge group, the matter spectrum, the superpotential, and none of these really need details of the geometry or the metric. They're usually cohomological calculations, or we can get at them with algebraic geometry. However, if we really want sort of honest couplings in the four-dimensional theories and the low-energy theories, we need the honest metric, as several other speakers have mentioned. Away from phenomenology, more generally, we might just want to know more non-BPS information about these spaces, such as the KK spectrum for understanding swampland conjectures in these compactifications, or even learning more about CFTs, for example, with 2,2 supersymmetry, away from special points in their moduli spaces, or not focusing on SUSY-protected quantities. So being able to calculate these numerical metrics and get more information about them sort of has a wide range of uses. So the sort of phenomenological setup that I'll be thinking about is just a heterotic string as usual, without any fluxes. If I take X to be some 6-dimensional internal space, I preserve minimal supersymmetry provided X is Calabi-Yau. And also in addition, I have some Hermitian-Yang-Mills connection, which I won't really be talking about today. I'm always going to be in the large volume limit, so there'll always be some semi-classical description in terms of geometry, differential geometry. And then, as we know, in a compactification, it's the geometry of this internal space that really determines many of the properties of the effective physics in 4 dimensions. For example, the spectrum of fields we see in the low energy theory really come from doing a KK reduction where we keep the fields that are massless in 4 dimensions or light. For example, matter fields in these kind of compactifications come from harmonic representatives of certain bundle valued cohomologies. And these are then what appear in the superpotential and the Kähler potential of the effective 4D n=1 theory. Since obviously X has a non-trivial Calabi-Yau metric, and the Laplace operator which determines these zero modes depends on that metric, we need to be able to solve explicitly for both for the modes, and thus we need the explicit Calabi-Yau metric. So this is sort of a rough outline of the rest of the talk. I'm going to review very quickly, because other people have done it very well, something about numerical Calabi-Yau metrics. Then I'll tell you how you can compute the spectrum of the PQ form Laplace operator on these spaces numerically, and give an example of the kind of data you can get from that. And then finally, I'll tell you what you can do with this kind of new data. And in particular, we're going to use it to study the finite swampland distance conjecture in complex structure moduli space. Okay, so let's get going. So a quick review of the Calabi-Yau basics, just for people. I'm going to be working on threefolds in 6 dimensions. Obviously, we all know that Calabi-Yau manifolds are complex scalar manifolds with a Ricci-flat metric. We know existence proofs for these kind of metrics, but there are no explicit constructions. Let's unpack this definition a little bit. Obviously, because it's Kähler, there's some Kähler potential that defines the Kähler structure on these manifolds. And taking 2 derivatives of it gives us some real 2 form, which is just the Kähler form. This Kähler form is non-degenerate, so it defines a volume, which I've called vol J here. Secondly, the vanishing of the first Chern class plus the SU3 holonomy of the Calabi-Yau just tells us that we have a nowhere vanishing closed 3-0 form. And again, this also defines a volume form for us. And we'll see why that's important in a second. So sort of the main example I'm going to be thinking about, but this generalizes to any complete intersection, is the family of Dwork quintics, Dwork threefolds. So this is a quintic hypersurface in P4, which is just defined as the vanishing locus of this particular quintic equation, where psi here is the complex structure parameter of the Calabi-Yau. Importantly, the 3-0 form omega can be determined exactly just from the information of the defining equation, and you can just write this down for whichever Calabi-Yau you're considering. All the information of the metric then comes from a choice of Kähler form, or in other words, a choice of Kähler potential. So in other words, given a choice of defining equation, your job is then to find the corresponding Kähler potential that defines the Ricci flat metric that's compatible with that 3-0 form. So let's imagine for a moment that you pick your favorite Calabi-Yau and someone hands you a Kähler potential and announces that it's Ricci flat. How would you go about checking this? Well, and as Sven mentioned, the basic idea is that you use the fact that on a Calabi-Yau, you don't actually need to check the vanishing of the Ricci tensor to check that it's Ricci flat. Instead, you can just compare the pointwise value of the volumes defined by the Kähler form and the complex 3 form all over the manifold. And if you found the honest Calabi-Yau metric, the Ricci flat metric, these two should agree, these two should be proportional with the same constant of proportionality all over the manifold. Using this, you can very easily cook up some functional of the Kähler potential, which just determines how close to being Ricci flat you are. And this is just a ratio of the volumes, which you then integrate over the manifold. The exact Calabi-Yau metric is then the one which has sigma is 0. So this gives us a way to measure how close we are to Calabi-Yau. Finding a Ricci flat metric then just reduces to finding a single function, the Kähler potential, that minimizes this particular sigma functional. So rather than try to solve for an arbitrary function, it's always helpful to have an ansatz, which gives you some control over the accuracy of the approximate metric that you're hoping to find. And the rough idea, as Sven mentioned, is to generalize a Fubini study type Kähler potential. Consider, for example, the space of quadratic polynomials on the P4 in which this Dwork family is embedded into. We can construct all the quadratic polynomials and then cook up something like a Fubini study type Kähler potential just by taking the inner product of these things with some Hermitian matrix of constants, which I've called H alpha beta here. At degree 2, so K is 2, there are 225 parameters in this particular metric, and this lets us parameterize the space of Kähler metrics within this ansatz. At degree K, the number of parameters you get goes up as K to the 4 on a threefold. So the higher values of K you take with higher degree polynomials allows you to input more and more freedom into this ansatz. The name of the game then is to figure out how to fix this metric H such that you get closer and closer to the Ricci flat metric within this space of ansatzes. So as we've heard sort of twice today already, and I'm sure many people are familiar with, there are 3 approaches to finding the sort of best Ricci flat metric, which you find by fixing this matrix of constants H alpha beta. There's an iterative approach first introduced by Simon Donaldson nearly over 15 years ago now, which basically solves for the balanced metric, which in the limit of large K gives you the Ricci flat metric. One might also try to just minimize sigma directly as a function of the parameters in this matrix H. And you can do that providing you have a lot of symmetry. And this is actually the technique we'll be using, so I won't say much more about it. Finally, you can use this sigma error as a loss function for a neural network, as Mike Douglas and collaborators and Lara Anderson and collaborators have done, and Sven talked about today. One can also try to find the metric directly instead of going via a Kähler potential or an ansatz, which is obviously going to be useful for studying non-Kähler backgrounds, for example, but you then need to impose Kählerity and some other conditions to make sure your metric is well defined. Obviously, I'm sweeping a lot of details under the rug here. I mean, you need to evaluate some numerical integrals here. You do that by Monte Carlo. You need to sample points on the manifold. You need on the order of millions of points to do these integrals with sufficient accuracy. But for the moment, these sort of details aren't very important. So with this in mind, this is sort of all to say that we now have a variety of ways to compute pretty accurate approximate Calabi-Yau metrics in a number of different ways. And you can imagine a day in the not so distant future where you'll just be able to download a Mathematica package to compute your favorite Calabi-Yau metric and then do what you want with it, right? So we might ask, what do we actually want to calculate with these things? And sort of the first obvious answer to this is what's the spectrum of the Laplacian on these spaces? As I mentioned at the start of my talk, there are many important phenomenological details of models that come from string theory that are determined by the spectrum of the Laplacian on these spaces, in particular the harmonic modes fixed to low energy physics. Ignoring the gauge sector for the moment, these harmonic modes are just PQ forms, which are eigenmodes of the Laplace operator delta on the Calabi-Yau manifold. And here I'm denoting the eigenmodes by phi with corresponding eigenvalue lambda, which are going to be real and non-negative because we're on some compact Calabi-Yau threefold. And in general, these things can appear with some non-zero multiplicities, which, depending on your example, come from continuous or finite symmetries. And we'll see examples of this. The harmonic modes are simply the eigenmodes with lambda as 0. Whereas for the higher massive modes with non-zero lambda, these things are proportional to the 4-dimensional mass squared of the excitation in a KK reduction on this manifold. So recall that in order to compute things like superpotential couplings, we actually need to compute triple overlap integrals of the normalized zero modes, for example. Thus, we actually need some way of computing both the spectrum of the Laplace operator on X and have access to the eigenmodes themselves in order to do calculations. So the case where the eigenmodes are simply functions was previously done by Volker-Braun and collaborators. And today I'll sort of tell you how this works for the whole spectrum of PQ forms. The rough idea is very simple, very familiar. Since the Laplacian preserves the complex type of a form, we can consider the eigenvalue problem for each choice of P and Q. And fixing a value of P and Q, we just pick some nice basis of PQ forms on the embedding space, on the P4, where nice in this case means easy to evaluate numerically. And this basis, these alphas, in general, will not be orthonormal. We can then expand any eigenform we like as a sum of the basis, where the inner product here will be determined by the Hodge star, which in turn depends on the approximate Calabi-Yau metric that you calculated as an input to this calculation. The eigenvalue problem for the Laplace operator, calculating the eigenmodes and the eigenvalues, then becomes a generalized eigenvalue problem for the eigenvalue and the eigenvector that just tells you how your eigenmode is built out of this basis of PQ forms. So you just evaluate some matrix elements and you get matrix elements of the Laplace operator and also something which tells you about the orthonormality of the basis you've chosen. Obviously, this is all fine in principle, but computers usually aren't very happy when you give them infinite dimensional problems to solve. So at this point, we have to make another approximation, and that's that we need to truncate this basis of PQ forms, alpha, on the embedding space to a finite approximate basis at some given degree. So in the same way as we used some degree k polynomials to compute an approximate metric, we do the same thing now with degree k phi basis forms in which we're going to expand our eigenmodes. And you should think of this roughly as just expanding your eigenmodes in terms of spherical harmonics on the P4. For example, you pick some PQ form of a given degree, and then, for example, if I take just scalars at degree k phi, I just recover the degree k phi polynomials. At degree 2, if I look at 1-0 forms, there's again some combination of holomorphic 1 forms up on the P4. And I can then tensor these things together. So I get some holomorphic piece, some anti-holomorphic piece, and then I divide through by some factor that ensures that this is well defined under the scaling on the projective space. As I increase k phi, the degree of the basis, I basically make the approximate basis larger. And this has sort of 2 effects. One is just that the basis gets bigger, so I can compute more eigenmodes, I can compute more eigenvalues. And also because I have more eigenvalues, the eigenmodes, because I have more basis elements, the eigenmodes I compute will be more accurate. They'll be better approximated in this approximate basis. So given these 2 bits of information, the name of the game then is just to compute the matrix elements of the Laplace operator and the inner product of the basis elements numerically using Monte Carlo and the approximate Calabi-Yau metric that you computed as an input for all the independent choices of P and Q on your 3-4. Given this, you just find the eigenvalues and eigenvectors and it will give you the spectrum. Now, obviously, it's kind of hard to know if you're doing the right thing if you just jump straight to Calabi-Yau. We don't have any data to compare to. You may just be spitting out random numbers and no one knows if it's correct. So it's instructive to start with sort of a toy example where we have control over what's happening. And for that, we can just consider the spectrum of the Laplace operator just on P3 with a standard Fubini study metric. So you have some given degree at which you want to compute this approximate basis in. You know the exact Fubini study metric. It's very simple to integrate over 1 million points in this case. And you can just compute the spectrum of the Laplace operator, in this case, very simply. So this here is a spectrum of the independent values of P and Q on P3. In blue are the eigenvalues one gets from this numerical input, from the numerical method. And the little black dotted lines are the exact values that you can calculate exactly using some SU4 representation theory. And in particular, one finds that you not only recover the correct eigenvalues, you also get the correct multiplicities, which again are predicted by some SU4 representation theory. As you take the number of integration points up to infinity, you better approximate the actual continuous structure of the manifold. And in that limit, you recover the SU4 symmetry. So what happens is that this little spread in the eigenvalues gets smaller and smaller and smaller until the degeneracies are exact. So let's go to a Calabi-Yau example. And the Calabi-Yau example we're going to consider is just the Fermat quintic. So we're going to turn off the complex structure modulus. I should say at the outset, just flashing a table of numbers isn't very instructive, but we're going to do something with this data later. So this was integrated over 3 million points at some given degree. This was all done on my own laptop. I'm sure you can do better than this if you have access to big computers. And you can just go away and run this thing for 2, maybe 3 days and produce the low-lying spectrum of the Laplace operator on the Fermat quintic. In particular, the scalar sector agrees with previous calculations by Braun and collaborators, whereas all these other values up here are sort of new. Again, you see some non-zero multiplicities, which I've called mu here, and you should think of these as coming from just the dimension of the irreps of a particularly large discrete symmetry, which is just the discrete symmetry that preserves the defining equation Q is 0 in this case. 2 things to note, which you sort of can take away from this. We know that omega and j should be harmonic modes on the Calabi-Yau, so they should give exact 0 modes. If I look at the 1-1 forms, for example, there's clearly a very low-lying 1-1 form here with a much smaller eigenvalue than anything else in the spectrum, but it's not quite 0. And that's to be expected. And one actually finds that as you increase the dimension of the approximate basis, this eigenvalue starts coming down and gets closer and closer to 0. In the case of 3-0, we again know that the 3-0 form omega should be an exact 0 mode. And this isn't actually doing too well. It's quite large, this eigenvalue. And this can be traced to the fact that for k phi is 3, the approximate basis that you have for 3-0 forms is actually very small. It's only 350 dimensional compared to on the order of 1600 for the 1-1 forms. And again, if you increase the size of this basis, this eigenvalue starts coming down. So if you really had a problem you were interested in solving, you could put this on a big computer and improve the accuracy of this thing. But you'd kind of have to have a reason to do it other than just being curious. So given that one can actually calculate this kind of data for Calabi-Yaus, you might think, what kind of information are we actually interested in? For example, maybe we're interested in understanding typical or average properties of the spectrum of a Calabi-Yau as a function of moduli. For example, what is the typical spectral gap in the moduli space of a Calabi-Yau? Does the full spectrum of a Calabi-Yau, averaged over moduli, possess any interesting statistics? And I'd like to propose that these kind of questions are actually important both for understanding the landscape of string compactifications and also the properties of the CFTs, which have target space Calabi-Yaus. Just on a very simple point, given that fixing moduli has been such a headache, maybe it is useful to have an idea of the kind of physics that is possible within the moduli space of a given Calabi-Yau compactification. Also, since the properties of 2D CFTs with Calabi-Yau targets are captured by the spectrum of the Laplacian on the target space, or at least in the large volume limit, the momentum modes, perhaps understanding sort of typical properties of Calabi-Yau spectrum would help us understand sort of typical properties of 2,2 or 4,4 CFTs. So as a sort of first step in understanding this, I can give you an example of the kind of investigations that one can do. So you can take a generic quintic threefold and just throw in some random parameters C sampled from the unit disk with a flat measure. You can then compute the metric and the spectrum of the Laplacian for this choice, and then just do this many, many times over and compute the resulting spectrum. If you do that, you then get something like an ensemble of Calabi-Yau data And here I've just shown the scalar spectrum for 1,000 samples. And this gives you some sort of Clavier statistics that you can start playing with. And in particular, this is non-BPS data, right? This is not data you can access via some supersymmetry calculation. A nice thing about this is, for example, that you can see if you just take sort of an arbitrary Calabi-Yau in this moduli space, the spectral gap, the distance to the first massive mode, is nearly always much smaller than that for the Fermat-Quintic, which you sort of expect based on symmetry grounds. And you can also just compute the distribution of the eigenvalues themselves higher up the spectrum. So in my last 5 minutes, I want to give you a very sort of concrete example of where you can use this kind of new data to really say something about physics or check something about physics. And that's going to be the swampland distance conjecture. So as we all know well now, the whole idea here is that if you have a theory coupled to gravity with some moduli space parameterized by vevs of fields, if you move an infinite distance in the moduli space, we expect it's going to bring down massless states that are going to ruin your original effective theory. And the finite version of this is just the statement that there should be some relation between the mass of this tower of states and the distance that you move in moduli space. In particular, if you move trans-Planckian distances, there should be some tower of exponentially light states coming down. More precisely, if I compare 2 points in the moduli space of a theory from some compactification connected by some geodesic distance d, where the geodesic distance depends on the moduli space metric, which I've called GAB here, the conjecture just implies that there should be a tower of states that becomes light on moving from P0 to P1, with some masses that depend exponentially and some coefficient which should be order 1, which I've called alpha here. So obviously, we can compute these things numerically. The conjecture doesn't tell you which states come down, but we can check it for the KK spectrum of states as we move around in complex structure moduli space. So you use a numerical metric and compute the spectrum of the Laplacian, and then just track the low-lying modes as a function of the complex structure parameter psi on this manifold. You need the sort of following ingredients. You need the moduli space metric. Fortunately, this was written down for this particular family by Philip and collaborators late in the 90s. The moduli space metric is known as a function of psi, and you can compute these things in terms of some hypergeometric functions, which solve certain Picard-Fuchs equations. Secondly, you need the geodesics themselves and the geodesic distances as you move around the moduli space. You have to solve the geodesic distance equation using some numerical shooting method, but you can do this, and you can then translate changes in psi to changes in geodesic distance on the moduli space. So for example, here is a plot of the moduli space metric as a function of psi on the complex plane. And in particular, we're going to be interested in this blue geodesic here, which is psi is real. Because for psi is real, the geodesics are just straight lines. So they're very easy to understand and very easy to check. I'm going to be focusing on the scalar spectrum, but obviously you could redo this for the whole P-key form spectrum. So here's the results that one finds. So on the left are the first few low-lying eigenmodes of the scalar Laplacian as a function of complex structure, as I crank it from 2 up to 1,000. Some comments, you always have a 0 mode, which should be obvious. And the multiplicities, which are given by mu here, are just given by the irreps of some reduced symmetry group, which is reduced because I turned on that complex structure parameter. Curiously, the eigenvalues with small degeneracy are those that become lighter, whereas the eigenvalues with large degeneracy become heavier. And in particular, there's also a maximum in the spectral gap around psi is 4. And at the moment, we have no real explanation for these behaviors, and it would be good to understand them better. So let's translate this to a question about geodesic distance. We use the moduli space metric and the geodesic equation to convert changes in psi to changes in geodesic distance d, and then we can just track how the mass of the KK modes changes as a function of geodesic distance in the moduli space. In particular, what you would call the second lightest mode at the original point is the one that falls exponentially with geodesic distance. And since the eigenvalue of this thing gives the mass squared of the corresponding KK mode, this just tells us that the coefficient with which the mass drops is about 0.45, which is indeed order 1 in agreement with the finite swampland distance conjecture, and almost saturates the proposed bound of David Andrew and collaborators. Interestingly, because it's the second lightest mode that comes down, you might be able to sort of have trans-Planckian field excursions because it's not the lightest mode that's then dropping in mass exponentially. It might be a mode further up the tower. But to better understand this, you'd really need to understand why these crossings occur, and in particular, which modes are the ones that become light for large psi in order to make any general predictions. So in the last minute, let me just sort of summarize and sum up what I've said. So hopefully you're sort of convinced now from my talk in the previous two that Calabi-Yau metrics are really accessible with numerical methods. And they're a new source of sort of interesting non-BPS data with applications in phenomenology, CFTs, and in particular, understanding swampland-like conjectures. And there's obviously much more to do and understand. So obviously, nearly everything I've said works for gauge bundles too. You can compute numerical connections. And if you start putting this all together, maybe you can compute superpotentials or Yukawa couplings at some point. On the CFT side, as I said, the Calabi-Yau target includes a lot of information about 2,2 or 4,4 field theories and large volume limits. And you might imagine that these kind of, the data of the spectrum might be able to use as sort of an input for things like the conformal bootstrap in these conformal field theories. Finally, if you cannot fix moduli, maybe understanding typical compactifications will help us understand the landscape of Calabi-Yaus, the distribution of Yukawa couplings, and then there are just more questions in geometry, like why do you see these eigenvalue crossings? And can, for instance, you understand anything about the SYZ conjecture using these numerical Calabi-Yau metrics? Okay, thank you.
Okay, thank you, Anthony, for a very nice talk. We have a few minutes for some questions, and I see some popping up fast. So, James, do you want to ask your question?
Hey, thanks. Yeah, you may have said this already. Could you go back to slide 13?
Yes.
I'm going to
Yes. Here we go.
childhood from the background, sorry. Yeah, I just had a question about accuracy. So if I look at those columns with the 3 form and the Kähler form in them, the accuracy of the 0 mode seems to be way off the plus or minus you're giving for everything else. So
the plus or minus here is I should have said this, sorry. The plus or minus is the spread within a cluster of eigenvalues. So, so when I write down a multiplicity here, there are 20 eigenvalues within one standard deviation of this value, for example, where one standard deviation is 0.2.
So in fact, the errors on those numbers are probably larger if we look at...
the actual errors on these things are going to be larger. And you can also tell this because there should be relations between, for example, the spectrum of 0,0 forms and the spectrum of 1,0 forms and the spectrum of 2,0 forms, based on whether certain things are exact or co-exact. So you can compare across and sort of see where where some modes are too high or a little low and so on.
Gotcha. So that sort of degree of error just seemed a little bit surprising because later on you managed to match its exponential so nicely. I mean, with these slightly different calculations.
So they're very similar. It's just the case that as you go to the non-scalar sector, the accuracy drops off very quickly.
Oh, I see. Okay, that's very clear. Thank you. It was a lovely talk. Thanks very much.
Okay, thank you. Next, Irena, if you want to ask.
Yeah, thank you. Thank you for the talk. Maybe it appears already in one of your plots, but what is I'm curious, what is the maximum gap that you can get? I mean, how far is from the Planck scale?
So I should say, and everything here is normalized so that the volume of the manifold is 1, so you have to put things back in. The maximum gap along this trajectory, at least locally, looks like it's here, right? So it's about 42. If you wanted to scan across the whole moduli space, and yeah, I don't know how to do that. It's a very large moduli space.
So this is 40 in units of the volume.
It's 40 in units of the volume, that's right.
Okay, so it's like 1 order of magnitude below.
That's right, yeah.
I see. And do you know if there is something special about the point in which the eigenvalues cross and you get this maximum gap?
As far as I can tell, there's nothing. So for example, the conifold point occurs at psi is 1 in these conventions. So psi is 4 is just some other random point here. And you also see, there are crossings of the other eigenmodes, just at other random values of psi. And understanding in particular why the lowest mode, for example, crosses over at this particular value will be very interesting, but I have nothing useful to say.
Okay, thank you.
Okay, great. So we have 1 minute and 1 more question. So Andre, if you want to ask.
Yes, thank you, Anthony. I wanted to ask, so do these crossings, are they related to the fact that an infinite tower of states has to come down and an infinite tower of states has to go up as you move in the moduli space? Because the situation is symmetric from the point of view of the first point and the end point.
Yeah, and assuming the states that go up and the states that go down are both both KK towers, then this would agree with that statement, right? And it will be interesting to understand why the states that come down when you move in this direction in moduli space seem to be the ones with the small degeneracies. But again, I have nothing useful to say. Yeah, that's a great point though.
Okay, very good. Let's all thank Anthony again for this very intriguing talk. Yeah, thank you. And